Hello students, I hope you all are doing good. Today we are going to discuss NCERT section 9.6 and example 9.8 of chapter Ray Optics and Optical Instruments. The disclaimer. Welcome to our session on Ray Optics and Optical Instruments. Today we will explore the fascinating world of light and how it interacts with different optical instruments. Our learning objectives will guide us through understanding the principles of light refraction and its application. Let's begin by setting the stage for what you will be able to do by the end of this lecture. The first learning objective is to understand the principles of light refraction through a prism. This includes grasping the geometric properties, the conditions for minimum deviation, and the mathematical relationships involved. It's crucial to comprehend how light bends as it passes through different mediums, which is fundamental to many optical technologies. Moving on to the second objective, we will apply these concepts to analyze ray paths and calculate refractive indices using the minimum deviation methods. This knowledge is not just theoretical, it has practical applications in designing and understanding optical instruments. By mastering this concept, you will be able to see how prisms are used in real world applications. Initially, we will discuss example 9.8 to highlight practical applications. The next topics in our index is refraction through a prism, labeled 9.6. This section will delve into how light bends as it passes through a prism, a fundamental concept in optics. Understanding this will be crucial for grasping how optical instruments like telescope and cameras work. So the problem asks to find the position of the image formed by a combination of lenses as shown in the figure 9.20. Understanding the arrangement and properties of the lenses is crucial to solving this problem. So begin with noting the focal lengths of each lens in the combination. This information is typically provided in the problem or can be inferred from the figure. So understand the type of lenses involved, for example, converging or diverging, as it affects how they bend the light. Then apply the lens formula 1 upon f equal to 1 upon v minus 1 upon u, where f is the focal length, v is the image distance, and u is the object distance. For each lens, determine the object distance first. For the first lens, this is usually given and can be assumed. For subsequent lenses, the image formed by the previous lens acts as the object for another lens. Remember to apply the appropriate sign conventions for lens calculations. Typically, distances measured in the direction of incident light are positive, and those against it are negative. After calculating through all lenses, the final result gives the position of the image formed by the entire lens combination. So let's start by identifying the given information for this problem. We have a combination of lenses and we will begin by looking at the first lens, which is a convex lens. For the first lens, we have some specific values. The object distance denoted as U1 is minus 30 centimeter and the focal length F1 is plus 10 centimeter. Our goal is to find the image distance V1. Okay. Now let's move on to the second lens in the combination, which is concave lens. We will need to consider its properties as well. So focal length f2 is known to us for concave lens, which is minus 10 centimeter, and we have to find the image distance, or the distance of image, location of image formed by the concave lens. Finally, we have the third lens, which is another convex lens. Let's see what information we have for this lens. So for the third lens, the focal length f3 is plus 30 centimeter. The image distance v3 will be the final image position that we are trying to find. Let's start by considering the image formed by the first lens. We will use the thin lens formula to find this image. This formula is essential in optics as it relates the object distance, image distance, and focal length of a lens. Understanding this relationship is key to solving lens problems. Okay, here is the thin lens formula. 1 upon V minus 1 upon V1 minus 1 upon U1 equals to 1 upon F1. In this equation, V1 is the image distance, U1 is the object distance, and F1 is the focal length of the lens. Each of this variable is measured in centimeters. This formula will help us to calculate where the image is formed by the first lens. Okay. Now let's substitute the given values into the formula. By substituting, we can solve for the unknown variable, which is in this case is the image distance v1. So after substituting the values, we have 1 upon v1 minus 1 upon minus 30 equals to 1 upon 10. Here the object distance u1 is minus 30 centimeter, indicating that the object is on the opposite side of the lens, and the focal length f1 is 10 centimeter. Solving this equation will give us the position of the image formed by the first lens. Okay, to find the v1, we have to put the value of u1 and f1. So u1 is minus 30. Why minus 30? Because object is placed on the same side from which incident light is coming. Okay, so object distance is measured in the distance against the direction of incident light. That's why it is taken as negative according to sign conventions. And focal length for convex lens is taken as positive, because focus is on the other side of the lens, and when we measure the focus, we measure in the same direction as the incident light. That's why f1 is equal to 10 centimeter. Okay, now solve this equation and find the v1, the image formed by the position of the image formed by the first lens. So here we have the equation for the first lens. 1 upon v1 equals to 1 upon 10 minus 1 upon 30. This formula helps us determine the image position by considering the focal length and object distance. Now let's simplify the equation. We subtract the fractions to get 3 minus 1 upon 30, which simplifies to 2 upon 30. Okay. Finally, we solve for v1, which equals to 15 centimeter. This box result indicates the image position formed by the first lens. It is important to note this value as it will be used in further calculations involving the lens combination. image formed by the first lens. Okay, so let's start by considering the role of first lens. The image formed by this lens acts as the object for the second lens, which is concave lens. This is crucial step because it sets the stage for understanding how lenses interact with each other. Now let's determine the object distance for the concave lens. The object is located 10 cm to the right of the second lens, calculated as 15 cm minus 5 cm. This distance is important because it helps us apply the lens formula correctly. Here we denote the object distance for the concave lens as U2 equals to plus 10 cm. The positive sign indicates that the object is virtual for the concave lens, which is a key concept in understanding how virtual objects are treated in optics. Okay, so positive sign with object distance indicates object is virtual for the concave lens. Although the image formed by the first lens is real, it serves as a virtual object for the second lens. This is because the rays appear to come from a virtual object for the second lens, highlighting the interplay between real and virtual images in the lens system. Okay, I will explain again. So what is happening here? So the object that is placed 30 cm in front of the convex lens. Okay, so image is formed on the other side of the lens at 15 cm, but concave lens is placed in between at 5 cm from the lens. Okay, so the rays that are being diverged by the first convex lens, that will fall on the concave lens. Okay, so rays will be, so that rays actually, if concave lens were not present, then that diverged rays will meet at 15 cm from the first convex lens, but concave lens is there, so that position of image formed by the convex lens will act as object for the concave lens. Which object? Virtual object, because it is not the real object. Image formed will be real, but in the path of the rays we have placed the concave lens, so that position of image will act as a virtual object for the concave lens. That's why we have taken U2 as positive 10 cm, because it is in the same direction of the incident light. The distance we are measuring, the object distance for the second concave lens, that object distance will be positive because we are measuring this distance in the same direction of incident light. Okay, so that is virtual object. Also for virtual object we take the object distance as positive. So though the image is real, but object is virtual, and that concave lens will form the image for that virtual object. Okay, so now we will see what is the position of image after the light rays refract through the concave lens. Okay, then that image formed by the concave lens will act as the object for third convex lens. Okay, then we will find the position of final image. Got it? So now we will begin by considering the image formed by the concave lens. Now we will use the thin lens formula to find the image position. Here's the thin lens formula: 1 upon V2 minus 1 upon U2 equals 1 upon F2. In this formula, V2 is the image distance, U2 is the object distance, and F2 is the focal length of the lens. So let's substitute the given values into the formula. We have 1 upon V2 minus 1 upon 10 equals 1 upon negative 10. Okay, this simplifies to 1 upon V2 equals 1 upon negative 10 plus 1 upon 10. Notice how the sign of the focal length affect the calculation. So solving this equation, we find that V2 equals infinity. This means the image is formed at infinity, which is significant result in optics. It indicates that the rays are parallel after passing through the lens. Okay. So let's start by considering the virtual image formed by the second lens. This image is at infinite distance to the left of the second lens, which means it acts as an object for the third lens. Here we define the object distance for the third lens as u3 equals to infinity. This notation helps us apply the lens formula correctly. In the next steps, remember when the object is at infinity, the rays are parallel to the principal axis. Now we'll use the thin lens formula to find the image formed by the third lens. This formula is essential for calculating the image position and is given by 1 upon 3 minus 1 upon u3 equals to 1 upon f3 equals variable. Each variable represents a specific aspect of the lens system. V3 is the image distance, U3 is the object distance, and F3 is the focal length. Okay, so let's focus on the application of thin lens formula. Since U3 is infinite, the formula simplifies, making it easier to solve for V3. Okay, I will explain that V2, the image formed by the concave lens, that is second lens in this combination. So position of image formed by this concave lens is infinite. So image is formed at infinity. So that image that is forming at infinity will act as an object for the third convex lens. That's why U3 is infinite. Okay. So image formed by the third lens. So now we are not taking minus infinity because it is minus 0 plus 0. It has no meaning. It is 0 only. Similarly, minus infinity plus infinity, that has no meaning, only infinity. Okay, minus infinity we can write, but 1 upon minus infinity and 1 upon plus infinity will automatically convert to 0. Okay, so it will not affect the result. So image formed by the third lens using the thin lens formula. So again applying the thin lens formula, 1 upon V3 minus 1 upon U3 equal to 1 upon F3. Now U3 is infinite, so we can put U3 equal to infinity. So 1 upon infinity will become 0 eventually. So it will simplify the equation. So 1 by V3 will be equal to 1 upon F3 simply. That means V3 will be equal to F3. Okay, so it will simplify the equation. Let's start solving the problem by substituting the given values into the lens formula. This step is essential because it sets the stage for calculating the image position. Pay attention to how we handle the values, as this will guide us through the solution. So now we have the equation after substitution. 1 upon V3 equals to 1 upon infinity plus 1 upon 30 equals to 0 plus 1 upon 30. Notice how the term 1 upon infinity simplifies to 0, which is a key point in optics when dealing with parallel rays. This calculation gives us V3 equals to plus 30 centimeter. This result indicates that the image is formed 30 centimeter to the right of the third lens. It's important to note the positive sign which tells us the direction of the image formation. To conclude, the final image is located 30 centimeter to the right of the third lens. This finding wraps up our example, illustrating how lens combination affect the image positions. Remember, understanding the sign and magnitude of the result is crucial in optics. Okay, so V3 came out to be plus 30 centimeter. That means image is on the right side of the third lens. So signs will play a important role in optics. So plus means it is in the right of the third lens at 30 centimeter distance. So here we have an image of a glass prism. Notice its triangular shape, which is crucial for its optical properties. This visual will help us understand how light interacts with the prism surface. So prism is a transparent optical element with flat polished surfaces. These surfaces are designed to refract the light, which means they bend the light as it passes through. This bending is essential for various optical applications. Triangular prisms are particularly important in optics. They are used to reflect light and can separate white light into its constituent colors, a process known as dispersion. This is why prisms are often associated with rainbows. As light enters and exits the prism, it undergoes refraction at both the surfaces. This dual refraction is what causes the bending and separation of light, making prism valuable tool in optical experiments and instruments. The angle of prism denoted by A is the angle between the two refracting surfaces. This angle plays a critical role in determining how much light will bend as it passes through the prism. The base of the prism is the third side opposite to the angle of prism. Understanding the geometry of the prism, including its base and angles, is key to predicting and explaining its optical behavior. Okay, so you can see in the diagram the surface in which light is entering and other surface through which light is exiting. So these two surfaces are bent and meet at one point. They have some angle between them. So that angle is known as angle of the prism. Okay, so base on which prism is lying. So that third side opposite to the angle of prism. Okay, so that is the geometrical properties of prism. Here we have figure 9.21, which illustrates a ray of light passing through a triangular glass prism. Notice how the light enters and exits the prism, bending at each interface. This visual will help us understand the path of light and angles involved. In this fragment, we see that light enters the prism at phase AB. The angle at which light hits the surface is called the angle of incidence, denoted by I. As the light bends inside the prism, it forms an angle of refraction R1. These angles are crucial for calculating the deviation. Now as the light exits the prism at phase AC, it encounters another angle of incidence R2. As it moves from glass to air, the angle at which the light emerges is called the angle of refraction or emergence, denoted by E. Understanding these angles helps us track the light's journey through the prism. The key concept here is the angle of deviation delta. This is the angle between the direction of the incident ray PQ and the emergent ray RS. It's measure of how much the light path has been altered by the prism. This deviation is what we will derive mathematically. Okay, so angle between the emergent ray RS and angle between the incident ray PQ is called the angle of deviation, as you can see in the diagram. Okay, so you can see the PQ ray is the incident ray and the dashed line is the normal to the AB surface. Okay, so angle between the normal to the AB surface and PQ incident light is I. Angle between the AC surface, angle between the normal to the AC surface and the refracted ray RS is the angle of emergence. Okay, and R1 is the angle of refraction at first surface and R2 is the angle of incident at second surface when light is going from prism to another medium. Okay, so the angle of deviation, how much incident light is deviated through its path when it exits the prism. So it is the angle between the incident ray and the emerged ray. That is the angle of deviation delta that we will calculate. We will do the derivation for angle of deviation delta. Okay, so let's summarize what we have covered. We have introduced the setup of light passing through a prism, identified the critical angles involved, and defined the angle of deviation. This sets the stage for our upcoming examples and further exploration of refraction through prism. So now consider the quadrilateral AQNR formed by the path of light within the prism. This shape helps us understand the relationship between the angles involved. We will use this quadrilateral to derive the formula for the angle of deviation delta, which is difference between the incident and emergent angles. So in the quadrilateral AQNR, the sum of the angles is 360 degree. This is fundamental property of quadrilaterals that we will use to establish the relationship between the angles. Specifically, we will focus on angle A, angle QNR, angle AQN, and angle ARN. So both angles AQN and ARN are right angles, each measuring 90 degree. This simplifies our equation significantly, as we can substitute these values directly into our angle sum equation. This step is crucial for simplifying the derivation process. Substituting the right angles into our equation, we have angle A plus angle QNR plus 90 degree equals to 360 degree. Understanding this relationship is key to mastering the concept of refracting through a prism. Okay, what is happening here? So we are taking quadrilateral AQNR. Okay, in that quadrilateral, so angle AQN. So this is the normal on the surface. That's why angle AQN will be 90 degree. Similarly, angle ARN will be 90 degree. Okay, so that two angles will be 90 degree and QNR is unknown and angle A is the angle of prism. So equation simplifies to angle A plus angle QNR plus 90 degree plus 90 degree equal to 360 degree. So after solving and rearranging the equation, so here we see the equation angle A plus angle QNR equals to 180 degree. This equation is derived from the geometry of the prism and the angles formed by the light's path. It's essential to grasp how these angles interact to affect the light deviation. Now let's consider the triangle QNR. This triangle is formed by the refracted light within the prism. Understanding the angles within this triangle is key to deriving the angle of deviation, as they directly influence the light's path. So finally we have the equation R1 plus R2 plus angle QNR equals to 180 degree. This equation ties together the refracted angle R1 and R2 with the internal angle QNR. It's crucial step in calculating the deviation angle, which we will use in practical examples later. Okay, now you can see in the triangle QNR, the sum of all the angles will be equal to 180 degree. Now you can compare these two equations, angle A plus QNR equal to 180 degree and R1 plus R2 plus angle Q and R equal to 180 degree. Now let's compare the two important equations, one stating that the sum of angle A and angle Q and R equals 180 degrees, and another stating the sum of R1, R2 and angle Q and R also equals to 180 degree. This comparison help us understand the relationship between the angles between inside the prism and the angles of refraction. So from our comparison, we derive the equation R1 plus R2 equals A, which is equation 9.34. This equation is fundamental in calculating the angle of deviation. Remember, each variable represents an angle within the prism, and understanding their relationship is key to mastering refracting through prism. Now let's talk about the total deviation denoted by delta. This deviation is the sum of the angles by which the light ray bends at both entry and exit faces of the prism. Understanding this sum is crucial for calculating how much the light path changes. Okay, so light is deviating at two surfaces. Firstly, it is deviating at AB surface. Okay, the light is refracting, so it is deviating through its path. And again, it is deviating through its path when it goes from prism to the surrounding medium at AC surface. So it is deviating two times. So net deviation delta is the sum of the deviations at both the entry and exit faces. So the formula for the angle of deviation is given here. Delta equals to bracket open I minus R1 bracket close plus bracket open E minus R2 bracket close. In this equation, I is the angle of incidence, R1 is the angle of refraction at first phase, and E is the angle of emergence, and R2 is the angle of refraction at the second phase. Each of these angles plays a role in determining the overall path of the light. So what is the first deviation? Deviation means through which angle light ray is deviated through its path. So at surface AB, you can see PQ, incident ray PQ is deviated through which angle? The angle MQR. The angle MQR. What is MQR? It is I minus R1. Okay, angle MQN. Angle MQN is equal to I. So subtracting R1 from I will give us MQR. That is angle of deviation at the first surface. Now, angle of deviation at the second surface. So QR. In the diagram, QR ray is deviating through some angle and emerged as RS. So the angle of deviation at second surface is MRQ. So angle MRN is equal to E. Subtracting R2 from E will give us MRQ. That is the angle of deviation at second surface. So sum of these two angle of deviation at both surfaces will give the total deviation, which is delta equal to I minus R1 plus E minus R2. So let's simplify the expression for the angle of deviation by rearranging the terms. We get delta equals to I plus E minus bracket open R1 plus R2 bracket close. This formula shows us how the deviation depends on the angle of incidence and emergence minus the sum of refraction angles. It's neat way to see the relationship between these angles. So delta will be equal to I plus E minus R1 plus R2 after simplifying it. To wrap up this section, remember that the angle of deviation is a key concept in understanding how prism affect light paths. This understanding is essential for application like spectroscopy and optical instruments. Next, we will move on to finding the angle of deviation in the terms of angle of prism. So now let's introduce the formula for the angle of deviation delta. It is given by the equation delta equals to I plus E minus bracket open R1 plus R2 bracket close, where I is the angle of incidence, E is the angle of emergence, and R1 and R2 are the angle of refraction at the two surfaces of prism. Understanding the relationship is key to predicting how light will deviate as it passes through the prism. So in this step, we substitute equation 9.34, which states that the sum of the angles of refraction R1 plus R2 equals the angle of the prism A. This substitution simplifies our equation and is a critical step in deriving the final expression for the angle of deviation. Okay, now we'll put the R1 plus R2 equal to A in this above equation. So finally we arrive at the simplified expression for the angle of deviation delta equals to I plus E minus A, as shown in equation 9.35. This formula allows us to calculate the deviation of light based on the angles of incidence and emergence, as well as the prism's angle. This understanding is the foundational for analyzing optical instruments that use prisms. Here we have the equation for the angle of deviation denoted as delta. It is given by the formula delta equals the angle of incidence plus the angle of emergence minus angle of prism. This equation is fundamental in calculating how much a light ray bends when it passes through a prism. Thus, the angle of deviation depends on the angle of incidence. The angle of deviation is not constant. It varies with the angle of incidence. This means that as you change the angle at which light enters the prism, the deviation angle also changes. This relationship is key to understanding how prism can disperse light into its constituent colors. To visualize this relationship, we have a plot that shows angle of deviation versus the angle of incidence. This graph depicted in figure 9.22 helps us see how the deviation changes with different incidence angles. It's a great way to understand the practical implications of the formula we just discussed. Okay, so here in figure 9.22, which illustrates the plot of angle of deviation against the angle of incidence for a triangular prism. Notice how the curve behaves, indicating the minimum deviation point. This visual representation is crucial for grasping the concept of light refraction through prism. Okay, so in figure 9.22, you can see the variation of angle of deviation with angle of incidence. Okay, so as we increase the angle of incidence, angle of deviation increases. Okay, to a certain value of angle of incidence. At particular value of angle of incidence, angle of deviation is minimum. Again, it starts increasing. So what is the interpretation of this plot? We will see. So look at the plot of angle of deviation versus the angle of incidence. Notice the two images here, figure 9.21 and 9.22, which illustrates the relationship as the light enters the prism. It bends and deviation angle changes depending on the angle of incidence. Pay attention to how this graph visually represents this concept. So for any given angle of deviation, except when the angle of incidence equals the angle of emergence, there are typically two corresponding values for the angle of incidence and emergence. This duality is important because it shows the symmetry of how light behaves when passing through the prism. Interestingly, the angle of deviation remains unchanged if we swap the angle of incidence and the angle of emergence. This symmetry is a key characteristic of light refraction through prism and highlights the predictable nature of light paths. So physically, this symmetry is due to the reversible nature of light paths. If you trace the rays backward in figure 9.21, you will find that the angle of deviation remains same. This concept is fundamental in understanding how prism can be used to manipulate light in optical instruments. Okay, So you can see in the plot that angle of incidence is equal to angle of emergence at a minimum deviation condition. Okay, so in the plot where angle of deviation is minimum, corresponding to that angle of incidence is equal to angle of emergence. For any other value except this, for any other value of angle of deviation except this, there is two values at which graph is intersecting. Okay, if we draw a parallel line to the x-axis from any angle of deviation except minimum angle of deviation, it will cut the graph at two points corresponding to angle of incidence and angle of emergence. Okay, so if angle of incidence is equal to I, then angle of emergence will be equal to I dash. If angle of emergence will be equal to E dash, then angle of emergence will be equal to I. Means they are interchangeable. If angle of incidence is equal to I, then angle of emergence will be equal to E dash. If angle of incidence will be equal to E dash, then angle of emergence will be equal to I. So they can be interchanged. So what is their physical significance? So we know that light rays follows principle of reversibility. If we reverse the path of ray at any point after experiencing number of refractions and reflection, the path of the ray is exactly reversed. It will trace its original path. Okay, so this is its meaning physically. So physically this symmetry is due to reversible nature of light paths. If you trace the rays path backward in figure 9.21, you will find the angle of deviation remains same. Got it? So at the angle of minimum deviation, I become equal to E. So at minimum deviation, the light ray inside the prism runs parallel to the base. This is a special condition where the deviation of the light ray is minimized. Understanding this condition is key to mastering how prism affect the light paths. Let's explore what this means in terms of angles and symmetry. The condition for minimum deviation is when the angle of incidence equals the angle of emergence, denoted as I equals to E. This symmetry implies that angle of refraction inside the prism are equal. R1 equals to R2. This is critical point to remember as it simplifies the analysis of light paths through prism. Finally, when the angle of deviation is at its minimum, we denote it as delta equals to dm. This is the point where the light path is most efficient through the prism. Understanding this concept is vital for applications involving prisms such as in spectrometers and other optical instruments. Let's begin by examining the relationship between the angle of refraction within the prism. Here we have R1 equals to R2 equals to R, which means the angle of refraction are equal. According to equation 9.34, the sum of these angles equals to the prism angle A. Now we can express the angle of refraction R as the half of the prism's angle A. This is shown in the equation R equals to A upon 2. This relationship is vital because it simplifies our calculation and helps us predict how light will behave as it enters and exits the prism in minimum deviation condition. Next, let's consider the condition where the angle of incidence I equals the angle of emergence E. From equation 9.35, we know that deviation angle delta is given by delta equals I plus E minus A. This relationship is key to understanding how the path of light changes as it travels through the prism. In this case of minimum deviation, the deviation angle dm can be expressed as dm equals to 2i plus 2i minus a. This formula is significant because it allows us to calculate the minimum angle by which light is deviated as it passes through the prism, providing insights into the prism's optical properties. Finally, we can determine the angle of incidence I in terms of prism's angle and minimum deviation angle. The equation I equals to A plus dm upon 2 gives us this relationship. Understanding this helps us predict the conditions under where the prism will cause the least deviation, which is essential for designing optical instruments. Let's start by applying Snell's law at the point of minimum deviation. This is where the refractive index of the prism becomes significant. Remember, Snell's law helps us understand how light bends when it enters a new medium, which is key to calculate the refractive index. Here is the formula for the refractive index. N21 equals to N2 upon N1 equals to sin I upon sin R. In this equation, N2 and N1 represent the refractive indices of two media. This formula is essential for determining how much the light bends as it passes through the prism. Now let's look at a more specific formula. N21 equals to N2 upon N1 equals to sin A plus dm over 2 upon sin A by 2. This equation, tagged as 9.38, uses the angle of prism A and angle of minimum deviation dm. It's precise method for calculating the refractive index of a prism. In this context, I equals to A plus dm upon 2 and R equals to A upon 2 as per equation 9.37 and 9.36. This step is about connecting the angles to the refractive index formula. Finally, this method provides a precise method to measure the refractive index of a given prism. Its practical application of the formula we have discussed, allowing us to accurately determine how light behaves in prism. Let's start by considering small apex angle and small deviations. In thin prisms, these conditions simplify our calculation and help us understand the basic behavior of light as it passes through. Here we approximate the sign of the angle as angle itself, which is valid for small angles. This simplification allows us to work with easier mathematical expressions and is common technique in physics. Similarly, we approximate the sign of half the apex angle as half angle itself. This step is crucial for deriving the relationship between the angle of deviation and the refractive index. Now, using these approximations, we can derive an important equation from our previous discussions. This equation relates the refractive index to the angles involved in the prism. So, refractive index denoted as N2. N21 is approximately the ratio of the sum of apex angle and minimum deviation to the apex angle. This relationship is key to understanding how prism bend light. This boxed equation shows that the minimum deviation dm is proportional to the product of refractive index minus 1 and the apex angle. This tells us how much the prism will deviate light based on its material and shape. In conclusion, thin prism do not cause significant deviation of light. This insight is useful in designing optical instruments where minimal deviation is desired. Let's now move on to the next section, application of prisms. So let's start by looking at how prisms bend light. This image illustrates the bending of light using prisms, which is a key principle in devices like periscopes and binoculars. Notice how the light path changes direction, allowing us to see around obstacles or magnify distant objects. This bending is due to refraction, where light changes speed and direction as it passes through different mediums. So next we have the concept of dispersion. Dispersion occurs because different colors of light deviate by different amounts when passing through the prism. This is why we see a spectrum of colors like a rainbow when light is refracted through a prism. Moving on to the periscopes, they utilize total internal reflection prism. This means that light is completely reflected within the prism, allowing us to see over or around obstacles without direct line of sight. It's a clever use of prism that demonstrate how refraction and reflection can be harnessed for practical purposes. Like periscopes are generally used in submarines to see the view outside water. Okay, so in first diagram you can see there is a red light which is entering, red color. So that is light ray, and that is the setup of periscope. Okay, so light is entering from one side, so that prism is known as poroprism. So what is happening here? Total internal reflection. Okay, so critical angle for glass, prism is made of glass, so critical angle for glass is generally around 42 degree, but you can see the light is incident on the slanted face of the prism at which angle? 45, which is greater than critical angle. So total internal reflection happens, so angle of reflection will also be 45 degree. So total deviation of this light will be 90 degree. And after falling on the second prism, which is on the downward direction, which is placed on the downward part, so again 90 degree deflection happens, and we can see the object or light that is coming from the upward portion. So this concept is used in periscopes in submarines to see the outside view of the water. Okay, so there is no direct line of sight. We have to bend the light 2 times by 90 degree deviation so to see the object outside. So these prisms, so light travels in straight line, so we have to use the prism and the concept of total internal reflection to see the object outside. So finally, let's discuss binoculars, which use poroprisms for image erection. This prism helps correct the orientation of the image, making it appear right side up to the viewer. This is essential for clear and accurate viewing, especially in devices designed to magnify distant objects. Understanding how prism work in binoculars give us insight into the engineering behind optical instruments. Okay, so the image formed by the lenses in the binoculars is inverted. Okay, to make the image erect, that poroprisms are used. Also to deviate the light through 180 degree, as shown in the middle diagram. Poroprisms are used in binoculars. So summary, this slide concludes with a summary that ties these concepts together, preparing students for practice questions and further exploration of refraction through prism. So let's focus on the apex angle of prism. The apex angle denoted as A is the angle between two refracting surfaces of prism. This angle is fundamental because it influences how light is reflected within the prism. Understanding this angle helps us predicting the behavior of light as it passes through the prism. Next, we have the fundamental prism equation R1 plus R2 equals to A. This equation tells us that the sum of angles of refraction equals the apex angle. Each variable represents an angle of refraction at the prism surface. This relationship is key to calculating how light bends inside the prism, and we will use it to solve problems involving light path. Let's discuss total deviation represented by delta. The formula delta equals to I plus E minus A shows that total deviation is the sum of deviation at both faces of the prism. Here I is the angle of incidence and E is the angle of emergence. This concept helps us understand how much the light ray is altered by a prism, which is essential for designing optical systems. Finally, we have the minimum deviation denoted as dm. Minimum deviation occurs when the light path is symmetric through the prism, meaning I equals to E and R1 equals to R2. This condition is important because it represents the least amount of bending the light undergoes, which often used in precise optical measurements and calculations. Now let's look at small angled prisms. Here the deviation can be approximated with the simpler formula dm equals to bracket open n21 minus 1 bracket close a. This approximation is useful for quick calculation when the prism angle is small. Notice how the deviation depends directly on the refractive index and the angle of prism. Prisms are not just theoretical, they have practical application in spectroscopy. They are used to disperse light into its constituent wavelengths, allowing us to analyze the spectrum. This is essential for identifying material and understanding their properties based on how they interact with light. Optical instruments like periscopes and binoculars utilize prism for image manipulation. Prism can invert or redirect images, which is crucial for these devices to function correctly. This highlights the versatility of prisms in various optical technologies. Finally, prism methods are highly accurate for measuring the refractive indices of material. This precision is vital in scientific research and industrial applications where exact measurements are necessary. Understanding these methods enhances our ability to study and utilize optical properties. So there are some practice questions. First question is, glass prism has an apex angle 60 degree and minimum deviation of 30 degree. Calculate its refractive index. Now let's move on to the second question. Here we are looking at a thin prism with a small angle and a known refractive index. The task is to find the approximate deviation angle. This is a great example of how the refractive index and prism angle work together to affect the path of light. For the third question, we are focusing on the concept of minimum deviation through a prism. Given one of the refraction angles, we need to determine the apex angle. This question helps us understand the relationship between the angles within the prism and how they influence light's path. Next, we have the question about a symmetrical ray path through a prism, specifically during minimum deviation. If we know the incident angle, we need to find the exit angle. This illustrates the symmetry in light's path when the deviation is minimized, which is a key concept in ray optics. Finally, let's tackle the fifth question. Here light enters the prism normally and we need to calculate the exit angle. This scenario highlights how refractive index and apex angle determine the light's exit path even when it enters at a perpendicular angle. So this is all about today's lecture. I hope you enjoyed the session. Thank you.